Threesome. Ready for a true coding interview classic? Threesome is a Pattern Mastery 100 favorite and a rite of passage for anyone prepping for phone interviews. It's notorious for tripping up even advanced candidates, partly because it demands both brute force insight and smart optimization. If you can solve threesome efficiently, you're mastering a pattern that unlocks dozens of top-tier problems. Let's break it down and see how the pros do it. Let's break down the challenge. Given an array of integers, find all unique triplets, A, B, C, such that A plus B plus C equals 0. The output must not contain duplicate triplets. The order of elements in the triplet doesn't matter, but each triplet must be unique. Now, let's assess our options. A naive approach would check every possible triple, O(n) cubed time. For interviews, that's a no-go. Instead, we'll sort the array and use the two-pointer technique. For each element, treat it as the first of the triplet and look for two others that sum to the opposite. Sorting helps us skip duplicates and efficiently scan for valid pairs, bringing us down to O(n) squared time. Here's the structure. We are given this list of numbers. Our goal is to find all unique triplets that add up to 0. First, we sort the array to make things easier. Now, we loop through the array one number at a time. At each step, we treat the current number as the first number of our triplet. We will look for two more numbers that add up with it to make 0. We place one pointer right after the current number. This is the left pointer. The second pointer goes at the end of the array. This is the right pointer. We add the current number, the left number, and the right number together. If the total is 0, we save the triplet. If the total is less than 0, we move the left pointer to the right. If the total is more than 0, we move the right pointer to the left. Now let's try to implement it using solution 1. We're defining a function called threesome that takes an array nums. First, we sort nums in ascending order, so we can use the two-pointer technique, and also skip duplicates easily. We create an empty array res. To store all valid triplets, we store the length of the array in n. Now we loop with I from 0 up to n-3, because we need at least two numbers after I to form a triplet. Before doing anything, we skip duplicates for I. If I is greater than 0 and nums I equals nums I minus 1, we continue, because we already processed the same starting number. Now we set two pointers. L starts at I plus 1, and R starts at n-1. While L is less than R, we compute the sum of the three numbers, nums I, plus nums L, plus nums R. If the total equals 0, we found a valid triplet, so we push nums I, nums L, nums R into res. After finding a valid triplet, we skip duplicates on the left side, by moving L forward while the next value is the same. We also skip duplicates on the right side, by moving R backward while the previous value is the same. Then we move both pointers inward, L++, and R minus, to search for another pair. If the total is less than 0, it means we need a bigger sum. So we move L to the right with L++. If the total is greater than 0, it means we need a smaller sum. So we move R to the left with R minus. Once the inner loop ends, we move to the next I. After the outer loop finishes, we return res. Time complexity is O of n squared. Because we sort once, then use a two-pointer scan for each I. Space complexity is O of one extra space, not counting the output, because we mainly use pointers and variables. Let's verify solution 1 for threesome. Input is nums equals -1, 0, 1, 2, -1, -4. After sorting, nums becomes -4, -1, -1, 0, 1, 2. Now we begin. At I equals 0, nums I is -4. We set L to 1, and R to 5. We try sums with -4. Total is -4 plus -1 plus 2 equals -3. Too small, so L moves right. Total is -4 plus -1 plus 2 equals -3. Still too small, so L moves right. Total is -4 plus 0 plus 2 equals -2. Too small, so L moves right. Total is -4 plus 1 plus 2 equals -1. Too small, so L moves right. Now L meets R, so we stop for I equals 0. At I equals 1, nums I is -1. We set L to 2, and R to 5. Now we test. Total is -1 plus -1 plus 2 equals 0. So we found a triplet, -1, -1, 2. We skip duplicates, then move L and R inward. Now L is 3, and R is 4. Total is -1 plus 0 plus 1 equals 0. So we found a triplet, -1, 0, 1. We move L and R inward, and the inner loop ends. At I equals 2, nums I is -1 again. Since it's the same as nums I minus 1, we skip it. To avoid duplicate triplets, at I equals 3, nums I is 0. We set L to 4, and R to 5. Total is 0 plus 1 plus 2 equals 3. Too large, so R moves left. And the loop ends. We're done. So we return -1, -1, 2, -1, 0, 1. The output matches the expected result, so solution 1 is correct for this test case. Now let's try to implement it using solution 2. We're defining a function called 3sum that takes an array nums. First, we sort nums in ascending order, so duplicates are grouped together, and results come out in a consistent order. We create an empty array res. To store all valid triplets, we store the length of the array in n. Now we loop with I from 0 up to n-3, because we need at least 2 numbers after I to form a triplet. Before processing each I, we skip duplicates. If I is greater than 0 and nums I equals nums I minus 1, we continue, because we already handled the same starting number. Now we create a set called scene. This set will store numbers we've already visited for the second pointer while scanning j. We set j to I plus 1, and start a while loop that runs until j reaches the end. Inside the loop, we calculate the complement we need. Complement equals negative nums I minus nums j. That's the third number required so that nums I plus nums j plus complement equals 0. If the scene set already contains that complement, we found a valid triplet, so we push nums I, complement, nums j, into res. Then we skip duplicates for nums j, by moving j forward while the next value is the same. Whether we found a match or not, we add nums j into the scene set, because it's now part of what we've scanned. Then we increment j, to continue scanning. After finishing the j loop, we move to the next I. Finally, we return res. Time complexity is O of n squared. Because for each I, we scan the rest of the array once with a set lookup. Space complexity is O of n. Because we use a set that can grow up to size n for each I. Let's verify solution 2 for 3sum. Input is nums equals 0, 1, 1. After sorting, nums becomes 0, 1, 1. Now we begin. At I equals 0, nums I is 0. We create an empty set scene, and set j to 1. At j equals 1, nums j is 1. The complement is -0 minus 1, which is -1. -1 is not in scene, so we add 1 to scene. Now j becomes 2. At j equals 2, nums j is 1 again. The complement is still -1. -1 is still not in scene. We add 1 to scene again, and j moves past the end. Now I would move to 1, but I is less than n-2 is no longer true. So we stop. We found no triplets, so we return an empty array. The output is an empty array, and the expected is an empty array. They match, so solution 2 is correct for this test case. Let's recap 3sum. This problem is a strong test of whether you can combine efficiency with careful duplicate handling, not just whether you can find numbers that add up correctly. The task is to find all unique triplets in an array that sum to 0. The challenge isn't only finding valid combinations, it's making sure you don't return duplicates, and doing it efficiently enough that it scales beyond small inputs. A brute force approach with 3 nested loops is far too slow at O(n cubed). The key improvement comes from sorting the array, which unlocks more structured searching. From there, using the two-pointer technique lets us find pairs that complement a fixed number efficiently, bringing the overall time down to O(n squared). The plan is, sort the array, then iterate through it by fixing one number at a time. For each fixed number, use 2 pointers, one from the left side and one from the right side, to search for the remaining 2 values that complete the 0 sum. Along the way, we skip duplicates both for the fixed number and for the pointer movement so every triplet remains unique. We implemented this successfully on LeetCode without errors by fixing each element in turn, moving the left and right pointers inward based on the current sum, and collecting results only when the sum hit 0. Sorting made duplicate detection straightforward, keeping the output clean without needing extra storage for uniqueness. LeetCode test cases confirmed correctness. For -1, 0, 1, 2, -1, -4, the algorithm returned -1, -1, 2, and -1, 0, 1, with no duplicates and all sums equal to 0. For 0, 1, 1, it correctly returned an empty list, showing it handles cases with no valid triplets as expected. The takeaway is that efficiency comes from structure. Sorting plus controlled pointer movement turns an expensive search into a clean O(n squared pattern, and learning to skip duplicates correctly is what makes the solution interview ready.